class. So this is actually last part of the derivatives. So we are done with chapter 1, 2, 3, 4, and then chapter 5 we are going to start the integral, which will be opposite operation of the derivative. So I want you to practice the derivative really rich. Then when we do backwards, then you will recall that derivative, okay? I'm telling you, it's only about a lot of practice. You will see the integral a lot better. So I want you to confident about derivative that when we do backwards, you can recognize the equation of your antiderivative. So which means we took the derivative, now you're gonna do backwards, okay? So which is chapter 5, but I will explain all those details. Today, we are going to study about Hopital's rule, and Hopital's rule is going to be really handy for finding limits, but there are some certain conditions that we have to consider. So let's look at our basic limit. So when we look at limit x goes to 5, how did we find? I know sometimes the limit gets a little bit tedious. What I do, I just plug in whatever they give it to me. And then if it doesn't work, I think about different ways. Should I rationalize it? Should I make a common denominator? Or what should I do? But first, just plug in. So when I look at this one, can I plug in? Yes. Why? Because it is a continuous function. Yeah. So all I need to do is just plug in 2 times 5 squared minus 3 times 5 plus 4. So the limit of continuous function is just by plug-in. I will get 50 minus 15 plus 4 is a 39. Hopefully that's the correct answer. Then, so we knew that if there's a continuous function, we can plug in automatically. Then we actually saw all of these questions in chapter 1. I just made a question. Now we can think about different way. What is the limit of this one? What are they asking? Anybody see it? So, Yana, can I plug in? So if you plug in this case, I think you will see what you get. So some of you guys don't see it, then you can approach as rational functions, and 3 goes to positive. That means they're asking asymptote. So you could think as asymptote, but Yana, there's no way I would think as asymptote. Then plug in 3 plus, that means 3.1, right? Then what happened? My number in bottom is going to be smaller, 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 or bigger and bigger and bigger. It's going to be 2 over 0, almost look like 2 over 0. So do you remember that the number over very small number becomes infinity, right? Becomes infinity. So same thing in here, same thing in here. You can think that this time if you plug in number 3 minus like 2.99999, then this time I get 2 over very small number, but I see that that one is negative sign. Do you see negative sign? So it becomes negative infinity. So I want you to think that some number over very small number, then it becomes infinity. 1 over very big number becomes what? It's gonna go close to 0, right? So now I want you to think about next 2. I already gave you a hint. What's gonna happen if I plug in this one? 2 over infinity. What would that be? 2 over infinity, 2 over 1 million. Then do you see that the number is getting closer to 0? So this limit will be 0 and that limit will be 0. But another way you can think is, are they talking about horizontal asymptote? Yes. Are they talking about vertical asymptote? Yes. So if you can see as a graph and see the asymptote, you can still approach. If not, plug in and deduce it, you're thinking of the numbers. So if you have a 1 over infinity goes to 0 and 1 over 0 goes to infinity, just don't forget we use a lot of the idea. Then how about when you look at this one, when I plug in, we get infinity over infinity. Then can I cancel out and say 1? No, we cannot say that in mathematics. So this one we have to find the limit a little bit better way. And how are we gonna find? Well, do you guys remember what they are asking before? This means x goes to infinity means they're asking horizontal asymptote. If you remember from pre-calc, horizontal asymptote 4 over 3. How did you get? Long division, right? Or just comparing that coefficient. But this time, if it turn out to be infinity over infinity, then we can apply Hopital's rule. Okay, what is Hopital's rule? If your function is going to be infinity over infinity or 0 over 0, then you can take a derivative. So I'm going to take a derivative of each. So if I take a derivative of top, that becomes 4, bottom 3. Bam! Do you see the answer? That is L'Hopital's rule. I used to call Hospital's rule. There's no S, Lo, and the H is silent, so L'Hopital's rule. That's how I pronounce L'Hopital's rule. So think about next situation. Also, they're asking about horizontal asymptote. If you see horizontal asymptote as a 1, that's very good. Very good. If you don't see it, then just take a plug in, then it turned out to be infinity over infinity. That means, can I use L'Hopital's rule? Yes. So I'm going to take a derivative. So that's going to limit x goes to infinity. Then I get 2x over 2x. That still gives me infinity over infinity. So can I take a derivative one more time? Yeah. So if I take a derivative, x goes to infinity one more time, 2 over 2, which is 1. That gave me my horizontal asymptote is going to be y is equal to 1. That's what we are looking for. So let's look at L'Hopital's rule here quickly. I will push up. So what is L'Hopital's rule? L'Hopital's rule is when the function is going to turn out to be, it has to be rational function, like a fractional. And when you have a limit, turn out to be infinity over infinity or 0 over 0, then you get to apply L'Hopital's rule. You get to apply L'Hopital's rule. Of course, denominator cannot be 0. So let's look at, there's in-class activities, and then it's gonna actually fun. So I want you to look at those 4. Plug in first if you can use it, and then answer for me and compare with me. Okay, so let's compare the answer. When do we use the L'Hopital's rule? When you plug in your x value, if it turns out to be infinity over infinity and 0 over 0, then you can actually take a derivative of top and denominator separately until you get the values. So when I look at first one, when I was trying to plug in and try to see that if I can use L'Hopital's rule, so plug in, and then I get infinity over infinity, so yes, I can use it. This one, 0 over 0, I can use it, and that's going to be 0 over 0, so yes, I can use it. This one, that's going to be 1 to the 0, I cannot use it. Then, but still there will be limit, so I'm going to take a derivative. So it turned out to be this way, and then simplify. I got this one, so as you see, if I plug in, this will be infinity. Also, if you see taking a long division, you see the top will be y is equal to x something, right? Then when you plug in the value of x goes to infinity, you saw that x has to be infinity. And your limit has to be infinity. Next one, so 0 over 0, so I took the derivative, that becomes a sine x over 2x, and then that still makes a 0 over 0, right? So I took the derivative one more time, then I got the cosine x over 2, so now with the limit 0, when x goes to 0, it will be 1 over 2. That will go to 1 over 2 as x approaches 0. And same idea, I have a 0 over 0, so take the derivative, then cosine x over 1, and I know that cosine 0 over 1 is 1 over 1, so that's how we get 1. Last one, if I plug in, I get 1 to the 0th power, 1 to the 0th power is 1, right? So that's the in-class activities, and then hopefully you understand the meaning in here. So let's look at our main dish, and we want to find the limit here. As you see, if I plug in straightforward, that's going to be minus 1, it's the 0th power, turn out to be 0 over 0, right? So this one turned out to be 0 over 0. So I'm going to try L'Hopital's rule and take a derivative of the top, e to the t minus 1. Bottom is going to be 2t. So let's plug in 0 again. Then I see that it becomes 0 over 0 again. So I'm going to take a derivative one more time. That will be e to the t over 2. Now if I plug in, I'm gonna get 1 over 2 as my limit. So you can take a derivative until, if it satisfies that condition, until you get the answer 2. Yeah. If it's 0 over 0 or infinity over infinity, you can keep taking derivative. B, this is pretty fun, right? B, now check what happens if I have an infinity in here. That is going to be 0. Okay, so if I plug in infinity, this is going to be e to the infinity minus 1 over infinity square. So You can actually say infinity over infinity because this one is going to be a lot bigger than linearly increasing too, right? So let's take a derivative that's going to be same thing. E to the t minus 1 over 2t, and then I'm sending infinity. Then that's going to be infinity over infinity again. So I can take a derivative again. That's e to the t over t2. Then if I plug in, this won't give me infinity, right? Because of that. So that goes to infinity. Young, why limit is so important? AI. Okay, when you guys do data science and then those AI developers and then who does a study, you always have to do limits. That's how you try to converge and merge around here. If it goes to infinity, you have to delete the cases. So you try to see the limit where it's going to be convergent to. Now there are two questions of in-class activities and I want you to try and then compare the answer with me. So how did in-class activity go? So for my answer, first one, I cannot use the L'Hopital's rule. When I plug in 0, turn out to be 1 over 0. Did you get that? But does that mean I don't have a limit? No, that's not true. That's only, you can use only L'Hopital's rule for that two cases. Then still you have to find the limit. So how are we gonna find the limit here? Then as you see, I can just separate them. You see that the function 3x over 8x I can separate plus e to the minus x over 8x, right? Because we had a rule that limit you can add or subtract or multiply. We can do that. So from here, as you see, if I separate the denominator, automatically that cancels out the left hand side. I get 3 over 8 plus, now let's plug in e to the 0 over 8 times 0. So what is this? That will be 1 over, what is this? 8 over 0 means a very small number. 1 over very small number becomes what? 1 over small number becomes very big number. So this becomes infinity. Okay, here that 0 is not 0. That means a point 0.00001. So 1 over very small number makes a huge number. So huge number plus less than 1. What would that be? That will be still huge number. So the answer for this one is infinity. So answer for this one as x approaches to 0 is infinity. Now look at B. It's the same question, but this time I want to find horizontal asymptote. So I plug in this one, turn out to be infinity over infinite. Do you guys know that e to the negative x actually goes to 0, right? If you look at the graph, it goes like this, so it's going to be 0. So infinity over infinity, then let's take a derivative. I get 3 minus e to the negative x over x. Careful, you have to do chain rule. Then I'm sending x to the infinity, e to the negative infinity. E to the negative infinity is this graph. So as you see, whenever it's infinity, this whole thing goes to 0. My answer, 3 over 8. I want you to also see that they are asking vertical asymptote. This one is a horizontal asymptote. So I want to see the graph here. I punch into Desmos again. And if you look at my graph, e to the 3x plus e to the negative x over 8x, do you see that this is 1? So your horizontal asymptote is going to be stabilized about 3/8. And then as you see your x approaches 0, you see that it goes infinity. So it shows that your graph shape is going to be that way. Okay, so let's continue our main dish. Okay, we want to find the limit of x times e to the negative x. Do you guys recall this one? We didn't see a lot, right? So when I plug in infinity, it's going to be infinity times e to the negative infinity. And I know that this is going to be this way. So can I use the L'Hopital's rule? No, it's not, but you have to actually see carefully what does the negative power mean. I can write it, this one as this way, right? Do you agree? Then I'm going to apply infinity. That makes infinity over infinity. Everybody agree? And now we can use the L'Hopital's rule. So you have to kind of manipulate and see that you can change into the form that it will fit if you could. If it doesn't, too bad, right? So I got infinity over infinity. So let's take a derivative that will be 1 over e to the x as the limit goes to infinity. Then what happened? 1 over e to the infinity is 1 over big number. What did I say? 1 over big number goes to 0. Yeah. we have talked about this one as a drug dosage, right? So basically it's gonna be peak at certain time of your critical point, and then it's gonna be go on to 0. Yeah, so that's what this means. So I want you to understand sometimes you cannot play right away, but you can manipulate a little bit. So let's continue to start. So we are going to do dessert, and this last part is actually came from our textbook 1.9 section. So if you look at 1.9, we approach this one everything using algebraically. So you can also check the answer, compare the answer over there. So now I want to see that can I evaluate this limit. So yes, you can do it algebraically, but also this time let's see if we could apply L'Hopital's rule. So as t goes to 9, and if I plug in, do you see that that becomes 0 over 0? So I want to see if I can just take derivative here. Then the limit t goes to 9, and take a derivative. The top will be -1. Denominator will be cancel out, negative. So I have to take a derivative of this one, right? So -1 over 2 square root of t. So from here, if I organize, this becomes plus 2 square root of t. Why? I just use it as a -1 divided by this means multiply by reciprocal. So I get 2 square root of t, 2 square root of t. So therefore, if I plug in 9 in here, I get 6. And compare the answer from up there. So then next one. I think that's correct. And then next one, same thing. If I plug in -4, it's going to be, you see that also it becomes 0 over 0, right? X goes to -4. Then this one, let's take a derivative. That means 1 over 4 plus 1 over x, and 4 plus x. So take a derivative of the top. Top will be that cancel out, and basically 1 over x. If I take a derivative, -1 over x squared. Then bottom is going to be 1, and limit goes to x as -4. So if I plug in now, that's going to be -1 over 16. And that's the answer. For me, sometimes it's easier to use L'Hopital's rule. Sometimes for me, algebra is fun to use too. So I wouldn't say that which one is better, but yeah, with my life, L'Hopital's rule was really easy. It was helpful. Okay, so now if you got the idea, there are 2 more questions of finding the limit, and that's what I want you to try. Okay, in class activities, and this is it for the last one. So when you look at this, I plug in, turn out to be 0 over 0. So I took the L'Hopital's rule. Watch my derivative carefully. This derivative is this one, and then bottom derivative is 1. So compare that, and then after that I plug in 7, and I got 1 over 6. B was a little bit tricky. If you want to take a derivative, it has to be chain rule, but when you look at this one, it's not easy to see. So I changed my chain rule to power as this one to the -1. Then you see that what I need to do, -1 brings it down, and then you're going to have a 3 plus h to the -2 power. So derivative of the first part is right here. I want you to compare, and the h derivative is 1. After that, I plug in 0, and it gives me -1 over 9 as my answer. And if you go back to 1.9 handout of the last page of the dessert, it's exactly the same question. You can compare that algebraically how you approach, and then you can use L'Hopital's rule for this one. Okay, so we're done with chapter 4, and then we're done with the derivative. So I'm going to help you understanding now what the integral is in the chapter 5 and 6 up to 7.1. Good job.